Good morning, everyone. This is going to be the fourth video in my series on the theory of computation. This is another prerequisite video. There are going to be a couple more, so I have others on graph theory coming up, as well as Boolean logic, strings and alphabets, and just some general proof methods in maths. So I think the textbook that I'm using effectively wants you to be quite competent in those areas and in writing proofs. Okay, so we're going to probably do a video on that. I mean, we'll see. But today, definitely, we're going to be talking about functions and relations. And this is I would say it's not really just elementary knowledge. Okay, what I was being taught today is not really just what is a function. Obviously we'll cover that, but there is some quite complicated stuff in terms of like theoretically what a relation is, and also things like equivalence relations, okay, and just some quite complicated terminology, right? So I would really recommend that you sort of, if you're confident with functions, watch this video in 2x speed, or maybe skip to certain parts, right? Because the beginning is fairly standard, but some of the stuff later on is a little bit more complicated. And my cat wants to say hi. Hey, honey. Hey. I know. Okay. Anyway, without much further ado, let's get straight into this. Okay, so here we go. Functions and relations. Okay. Hey. Also, I'll probably decrease the thickness of this pen, actually. I don't know why my cat is just being very, very happy right now. Maybe the better strategy is to just zoom out. Actually, that's okay. That's good. That's fine. Right, functions and relations. Okay. No. Right. Okay, so I guess the first question is, well, first of all, we'll talk about functions, because they're probably more well understood by sort of the general populace, at least coming into university level courses. And they're pretty much fundamental in maths. Probably sets are more fundamental. And functions are kind of, well, can definitely be spoken about using sets. So they're sort of the next level of fundamental art, but they're still fundamental. They're still very, very fundamental, I would say. And like, yeah, if you've done any secondary school, high school level maths, you've seen them, okay? And so we're going to discuss them here as a prerequisite to the theory of computation, right? Okay, so what's a function, first of all? Well, a function is effectively an object, okay? So you know how we're talking about you can put objects in sets. It's not unreasonable to therefore say that you could also put things like functions inside sets, right? Because it's an object, okay? So that term object is very loose, very open to interpretation, right? And in this case, it is acting as an object, right? Well, not just in this case, it is an object, okay? So a function is an object that sets up an input-output relationship, okay? And yeah, obviously, I'll explain a little bit what I mean by that. It's not the cleanest definition, but if you know what a function is, that should make sense to you. If you don't, then I'll explain what I mean by that, right? So really what I mean here, first of all, it's an object, okay? So that's just, that's just asserting that it's an object. And the fact that it sets up an input-output relationship is effectively me saying that a function will take some output and spit out an input. Take an input and spit out an output, right? So basically, a function takes an input and it does something to that input, and then it produces an output, okay? And produces an output, okay? So far it's very theoretical. There's no real way for us to ascertain what the output is going to be given that input, right? But we'll talk about that in a bit. But just theoretically, a function just is an object that sets up an input-output relationship, because when you plug some input into your function, it will do something to that input and then produce an output based on the input, okay? So we have this notation that if f is a function, right, whose output is b when the input is a, right? So if I input a into my function and it spits out b, then when the input is a, right, then the notation that we use, or we say that effectively f of a is equal to b. So that's how you read that, right? And I'm sure that you would have probably seen this sort of notation before. F of a is equal to b, right? So all this notation is saying is that effectively, so I should probably make this so that it's auto, because it puts it in white, but I should really put it in black. I'm not sure if I can fix that at the moment. I don't want to waste too much time. Oh, here we go, maybe. Okay, don't know why that's sort of whatever. That'll do. So ultimately what this is saying is that I take some input, right, a, okay, so this is like my input. I plug it into my function, so that's why I have f of f in the brackets around the a, right? And then I produce this output b, okay? And this is just notation for the function. Okay, so f is a usual notation for a function, or g, right? So you might see like f of x, I'm sure you're familiar with that, g of x, things like that, okay? That's just in general for any x that I'm allowed to input into my function. Then you might see it written as f of x equals something. So that tells me what happens to my x when I input it into my function effectively. That's how we would sort of typically denote functions at a high school or secondary school level. So hopefully that makes sense. But in this case, obviously, we just have f of a because we're talking about one specific input, right? So f of x is for just a bunch of inputs that we allow from some general set. And then f of a is for some specific input. Okay. Another way to describe a function. So a function might also be called a mapping. Okay, so that's just effectively just another word that we use to basically mean a function. Okay, so a function might also be called a mapping. So if you see someone say a mapping, they really mean it's a function. If you see someone say a function, then effectively it's the same as a mapping, right? Okay, and so obviously then this sort of term map then can sort of translate to the notation in that if f of a is equal to b, then effectively we say that f maps a to b. F maps a to b. Right, so effectively that's just the same thing as what this notation here is saying, in the sense that when I plug in some input to my function a, I get an output of b, right? But it's just saying it in a different way. It's just like sort of the written explanation of it, and it's sort of a more mathematically nice written explanation of it. Because obviously you can say it's a function whose output is b when the input is a, or you can just say that f is a function that maps a to b, and like this is sort of more nicer, more used, definitely more used mathematically, right? Yeah, I mean, it's just another way of saying basically what we've been talking about. So nothing too crazy there. You know, there are certain functions that you might have seen before, okay? And one of them is called the absolute value function, so just as an example of a function. So the absolute value function, right, effectively takes a number, okay, x as an input, right? So it's basically a function where your input is just some arbitrary number. Okay, I know that I obviously haven't specified, whether it's complex, whatever. Doesn't necessarily matter. Actually, it does matter because the complex would be slightly different. So just take it to be a real number, or say an integer. I think we deal with it as an integer here anyway. So it takes a number x as an input, right? And the function will basically branch out and do two different things depending on whether x is positive or negative. So, and effectively it returns x if x is positive, and minus x if x is negative. Sorry about my cat, by the way. Okay, so this is the rule of the absolute value function, right? So we're talking about how do you ascertain necessarily what an output is. So this is one way you can ascertain an output, is by me basically explaining the rules to you. Similarly, there's, if you were to have a board game in front of you, one way you could play it is by me explaining the rules to you, right? This is basically, well, that's really how you play it, right? Or how you understand how to play it, right? So this is how you understand how the function works, by me explaining it to you. It's kind of like a rule set, right? Just for a specific function. You might also see, obviously, with the absolute value function, we typically shorten it to sort of this. So abs here, that's basically just me representing the absolute value function, okay? So effectively what we can say is that abs of 2, right, is going to be equal to 2, right? So this is kind of like my f, right, from before. So I'm saying that f of 2 is equal to 2. But instead of f, because that's general, in this case I actually know the name of my function, and we call it abs. So abs of 2 is equal to 2, right? And it's kind of like abs, yeah, whatever. But effectively, and the reason why that is because this is x, right? Then effectively we know, and 2 is positive, right? So because 2 is positive, then effectively when I plug it into my function, I just return x, so I just return 2 again. Okay. Similarly, we can ascertain that abs of minus 2, okay, is also 2, because this is negative. Okay, so because it's negative, I have to spit out minus x, and minus x is just 2. Okay, so one thing that we'd be able to ascertain here is that effectively abs of 2 is equal to abs of minus 2, which is equal to 2. Okay, and in general, it is true that abs of x is equal to effectively abs of minus x. Okay, this is just a general thing. Yeah. which should make sense, right? Because if x is positive, then abs of x is just x, and then abs of minus x is going to be minus minus x, so that just gives you x, right? And if it's negative, then abs of x will be minus x, and abs of minus x will be minus x, right? So you get the same result. But I mean, that's just that didn't actually include that in the notes. It's not an important fact, but just as an example of a function, you have the absolute value function. Another function that you're probably familiar with, although you might not necessarily have regarded it strictly as a function, is addition. Okay, so addition is another function. Addition is another function, and we denote it with the sort of three letters add, written add, right? So what do we input to the addition function though, right? Because obviously, if I were to sort of try using this notation, f of a is equal to b, that sort of, what really is that input in this case, right? Because with addition, I can't just input one thing, because then I have nothing, I can't do any addition with that, right? Because just if I give you a number, you can't add it to like you need two numbers to add them, if you know what I mean, right? I can't just give you one number, you can't add one number, if you don't have anything else. So in this case, actually, the input to the addition function, right? Obviously, the input to the absolute value function is just an integer in this case, right? So we could say that effectively, yeah, our input is an integer, right? But in this case, addition you can't just take an integer by itself as an input. So actually, what we take is an ordered pair. Okay, so the input to the add function is an ordered pair of numbers. Right, and the output is just going to be the sum of those numbers, right? We're not worried too much about necessarily the rules behind that, just more that if we know how to add numbers together, then the output would be the sum of those two numbers, right? Okay, and the output is the sum of those two numbers, right? Okay, and the reason why the input is an ordered pair, right, is because effectively we need two numbers to be able to add them together, right? So addition at any one point in time, we'll say, is just a function that acts on two numbers. So effectively, if I were to give you the ordered pair 3, 4, then and I plug this into the addition function, so I do add of 3, 4, that will give me 7, right? Because I'm plugging in an ordered pair 3, 4, and it's adding those two numbers together, right? Obviously, one of my numbers could also be negative, right? In which case you technically get subtraction, but it's also addition, right? So if I were to do add of 3 minus 4, then obviously you would get minus 1, right? Because it's just adding those two numbers together. So if we know how to add two numbers together, then we can define this function called the add function, right? Which effectively just adds them together, right? And so the input is always going to be an ordered pair. We need to input two integers, and the output will be a single integer, right? Which is just their sum. Awesome. Okay, so I think it's about time that we have this more precise sort of wording for things, okay? So what we say in maths is that the set of all possible inputs, okay, of all possible inputs to a function, right, is effectively called its domain. Okay, so that's another term that I'm assuming that you probably would have covered at secondary school level, is that term domain. Okay, so the domain of a function, okay, is effectively the set of possible inputs to it, right? So the things that you're allowed to input into your function, right? Okay. And then obviously our function will output certain things. Okay, so we say that the outputs. Sorry, I wrote this in red. We say that the outputs of a function come from another set, and we call that set the range. The outputs of a function come from another set known as the range. Right. Okay. So again, just going back to notation. If we have a function f, so if f is a function, right, with some domain, and we'll call that domain. Obviously, that domain is a set, right? It's the set of things that we're allowed to input to our function, right? So if it has a domain set of capital D, right, and a range set of capital R, right, then the notation for effectively saying this, then the notation for saying this is simply f and then sort of colon, and then there's sort of capital D with an arrow pointing towards the R. Okay, so this is just this is the notation for saying that f is a function with domain D and range R. Okay, and so the arrow here, you can think about it, it's basically just saying that our function is taking an input from our domain set, capital D, and it's just like sort of doing something to it, and it's like taking it to our range set. Okay, what exactly it's doing is unknown, but theoretically, right, what a function really is just something that you give an input to and it spits out an output, right? Um, so this is how we basically say that, right? This is how we say I'm going to give it an input from this set and it's going to spit out an output from this set, right? So this is just and you typically always include this, right, with your function, right? If you were to specify what exactly your function is doing, right, you'll always also include this information, right? In other words, the input set which you're allowing, your inputs to be from to your domain, and also the range set where your outputs live. Okay, so you pretty much always include that with your function. Okay, so this is quite fundamental in terms of functions, right? Pretty much, yeah, a function is really defined in some sense by this notion that it has a domain set and a range set, and it's less so actually defined by what it does. Okay, because what happens in between there doesn't necessarily define a function, because many functions exist where there is really no rule, or there is some element of randomness. So, but even in those cases, there will be some domain and some range, right? You'll get an input, you'll see an output, but you won't necessarily know what's going on in the middle. So, yeah, that's that. That's a little bit of a tangent. So, what if you wanted to sort of look at this concretely, this concept of domain and range, but with a specific function, right? So let's look at it with the absolute value function. So, the domain and range of the absolute value function abs is effectively sorry, I was going to put the real numbers, but technically you could do it with, right? But in this case, we'll say it's the integers because that's what the textbook went with. Okay, so obviously, you could plug a real number into your absolute value function, and if you go back to the rule, there's nothing necessarily that is not allowed with doing that, right? Because obviously, all it does, it's a very simple function, it just spits out the same value if the input is positive, and it just plugs the negative, just sort of slaps a negative sign in front of the value if the input is negative, right? So, I mean, really, you could plug a real number like 2.4 in there, right? And you just get 2.4 out because it's positive. But I plug in minus 2.4 again, I get 2.4 back out because I just slap a minus sign in front of it. So obviously I could define it for real numbers, but we'll talk about it in for now, sort of effectively only for integers. So effectively, a domain or the set of inputs that we allow, right? Because obviously it's not necessarily like we could have other input sets, right? I could only allow, for example, natural numbers to be my inputs, or real numbers, right? Or anything for which the function works, I could allow that to be my domain set. Okay, so really the domain set is just the set of inputs which we allow, okay, which in this set is the integers. And then obviously once I have an integer and I do this sort of absolute value process to it, right? So I either spit out the same value that I input if it's positive, or just slap a negative sign in front of it if it's negative. Right, once I do that, I'm just going to get another integer, right? Specifically though, right, it is going to be greater than or equal to 0, right? Obviously, I haven't actually said what happens if you do substitute x equals 0 into this, but you can easily extend it, right? And this is what we do in practice to say that it returns x if x is positive or 0. Okay, so if you plug in x as 0, it just spits out 0. Okay, and it doesn't even matter. You could even put minus x if x is negative or 0, right? Because in both cases it gives you 0. So the absolute value of 0 we could define to be 0, and then in every other case, if it's negative, you slap another negative sign in front of it, so you make it positive. And if it's positive, you just keep it the same, so it's still positive. So actually, it won't necessarily be the range won't necessarily be the integers in the sense that it won't necessarily hit every integer. It will only hit the positive integers, right? And 0. But nonetheless, we can still work with that as a range set because it is still every positive integer or 0 is still an integer, right? So that's fine. That's good enough as a range set. Okay. So we write. Actually, I should really put that. It doesn't really follow through if I do it like that. So I say so we write, right? Effectively, abs from the integers to the integers. So the absolute value is a function whose domain is the integers, okay, and whose range is the integers. This is the domain and the range. And obviously, you don't necessarily need a rule, but obviously the rule is well known for the absolute value as well, right? Okay. Okay. But this is just me effectively showing how we sort of write formally things like how we specifically display the domain and range of a function, in this case the absolute value function. Right, what about for addition? Okay, well, for addition, we have effectively what we can say is that addition is a function whose domain is actually the sort of Cartesian product of the integers, because you're going to be inputting an ordered pair, right? And then your output is going to be an integer, right? So, you might be a little confused about this, but if you've seen my previous video and you're familiar with the Cartesian product, then you should understand why this is. The Cartesian product will always output an ordered pair, okay? And the first element of that ordered pair will be an integer, and the second would also be an integer, because these are the same set. So taking the Cartesian product, or cross product of sets, effectively of two of the same sets, right? Just the integers, right? So effectively, what you're going to get is an ordered pair, or effectively just two integers, right? Right? Because the Cartesian product just gives you all possible ordered pairs of integers, and effectively one of those will be your input, but your set of all possible inputs, right, or at least the ones that we allow, is going to be the Cartesian product of the integers, right? So you could also allow the Cartesian product of the real numbers if you want to do like 3.4 plus 2.1, right? But again, we don't do that for this, okay? Just it's an arbitrary choice, okay? So even though I could change this to, you know, R sort of cross R, but I can't just change this unless I change this, okay? Because if I said, well, I guess actually I could. That's a lie. I could put this as the real numbers, because obviously every integer is also a real number, so it's fine anyway, right? But that's not necessarily true always. You just need to be a little bit careful because the range has to include, at the very least, everything that is actually going to be output, right? Like if I have the function that squares an input and produces an output, right? Then obviously my outputs, right? They are going to be sort of positive or zero, positive numbers or zero, right? And if I plug in an integer, then I always get an integer out, okay? Specifically, I'm going to get a positive integer, right, or a zero out, right? So I could have my range as the set of positive integers, and just add zero into the set as well. But I can't have my range or my output set as a set of negative integers, right? Because then I don't even have, I mean, that's not right, because every input will not be mapped to a negative integer, right? In essence, the integers that I'm plugging in, right, none of them are going to be negative integers, right? And they're actually going to be positive integers or zero, but I haven't even included that in my range. So I need to, at the very least, include the positive integers or zero into my range. Then I can make it bigger, right? So I can effectively include the negative integers as well, okay? But I can't include the negative integers by themselves because I don't even have the bare minimum, which is what actually happens, which is that the numbers get sent to the integers, the positive integers or zero. Okay, but in this case, it's actually fine. You could change that Z to an R and still keep it as Z cross Z. That's fine. But it's just, you know, we don't really do that. But, you know, I guess theoretically, it's fine. Right, and this is sort of what I was just saying, what I want to add now. So a function might not necessarily map to or use all of its range. So a function might not necessarily use all of its range. Okay, so if the range is a set of integers, it might only actually ever use, or might ever actually only sort of, it might only map inputs to positive integers, even though my range is the set of all integers. Okay. So as an example, right, the absolute value of some input x, right, if I define it using this sort of domain and range up here, the absolute value of some input x equaling -1, right, never occurs, right? Even though, right, the range is the integers and -1 is an integer. Okay, so actually, not my entire range is not hit in that sense. It's not really used. But that's okay, right? That's fine. We're just stating here that it's not necessarily always true that the range is used, okay? But there's a name that we have for a function that does actually utilize all of its range, okay? So a function, right, that does utilize all of the range is said to be onto. That does utilize all of the range. All of the range is said to be onto. So that's special notation there, right? Or special wording. So if I have a function, right, let's say that it's the function that takes, well, actually, let's just say the absolute value since that's what we already have, right? So in this case, the absolute value, right, if I have the integers as my domain, right, and I actually have my range as the set of positive integers, which we typically write as z plus, and then I add, so I union that with the set containing the element 0, right, then this is actually onto this function, okay, by that definition, because my range set is effectively utilized, right? So every single thing as a positive integer or 0 will have a corresponding input, right? In other words, if I input an integer, I'll always get a number, right? Effectively, every output I get will be in the set sort of positive integers union 0, right? And I'll get all of those sort of outputs from that set effectively, right? So if I were to choose the number 1, which is in this set of positive integers union 0, then obviously I can find an input effectively that gave me that output, right? And I can do that for all my possible outputs. So actually that is onto, right? So actually, really, the function being onto is kind of dependent on what we choose as the range. Okay, so obviously this function here that we had before is not really onto. It's not onto because of the reason I just said, right? Absolutely, -1 never occurs. But this is, even though it's the same function. So you need to it's really just a choice of ours. It's not really an inherent property of functions, really. Sort of our own choice whether it's onto or not, right? But we typically like to make functions onto, and also something we call injective, so that they have an inverse. Okay, but that doesn't really matter for this course. What really matters is just this concept of onto, okay? Because that was mentioned. Okay, you don't need to worry about the term injective, but it really just means one-to-one. So effectively, no two inputs are mapped to the same output, right? In this case, that does happen, right? Because, for example, -2 and 2, they both map to 2 when you plug them into the absolute value function. But for other functions, that doesn't happen. And then we say that they're injective. And any function that's injective and onto will have an inverse function, okay? So you'll be able to go back from the output to the input, effectively. But that doesn't necessarily matter for this case, okay? Don't worry about that. Right. Awesome. Okay. So there are a few ways, for our sake, that you can describe a function, okay? And pretty much, I think, definitely within these notes, all the functions that we talk about have some algorithm to produce an output. Although, technically, it's not required. All of the functions that we'll talk about have an algorithm to compute an output, okay? Actually, yeah, pretty much all of them will. Although some of them, the algorithm won't necessarily be stated very clearly. But they're not necessarily randomly generated outputs, right? Random, but you know what I mean. Like, the output's not necessarily just picked from some sets arbitrarily, okay? But rather, there's typically some algorithm or procedure that gets us to those, okay? So we're really talking about functions where you just, yeah, basically the functions that we talk about won't be too exotic, they won't be too funny. But, and so whenever we describe a function, we'll talk about really an algorithm, or we'll give a table of values, as I'll talk about. So there are a few ways, right, to describe a function. Okay, so one way is with a procedure. So one way is with a procedure, right, for computing an output from a specified input, right? Okay, so for example, if I were to give you an input and the procedure was that you square that input to produce an output, then that is a valid way to describe a function. Right? You could say this is a function with a domain and range of the integers per se, such that effectively your output is generated by squaring your input. That's a fine way to describe a function. Okay, another way to describe a function is via a table, effectively listing all possible inputs. Okay, so obviously this only really works sometimes, because you can't necessarily do that for all functions, definitely, right? Because there are some functions where you're inputting infinitely many things, right? If my domain is the set of integers, right, then there's infinitely many integers, so I can't list all possible outputs. Sometimes you can. Oh well, yeah. So yeah, this is saying listing all possible inputs and then stating the outputs for the inputs. So it's saying the same thing that I'm saying, and stating the outputs for each input. Okay, so let's just look at an example. For example, let's look at an example, right, of sort of a table, right, that you might use to generate a function. Okay, so yeah, in practice, obviously, I haven't really seen these very much. Typically, what you see is just more a sort of rule, right, like f of x equals x squared, for example, right? But it is possible to describe a function this way, so that's okay. So consider the function effectively f, and the domain that we're going to be using is the set of integers from 0 to 4, right? And our range will be the same set, so the set of integers from 0 to 4, right? Described below. So you might have a table like this. You have n, f of n, then we have 0, 1, 2, 3, 4, right? And actually the output values, we just state them, right? Because there only actually ever 5 inputs. Right, the only thing I could input into my function is any element of the set, right? So it could be 0, 1, 2, 3, or 4. So there's only really have 5 possibilities. And so I just state the output for each of those cases. So actually it's going to be 1, 2, 3, 4, 0. Okay? So this is just one way of stating a function, right? We're defining a function basically based off of, we're just stating all the possible outputs, because all the possible inputs, there's only ever 5 of them. So it's not really hard work to do that, right? It took us quite quick, like a few seconds to do. But actually, there is actually a sort of a procedure as well to compute f of n if this is the f of n values for this set of n. Okay, and effectively, that would be the following. So the f of n is equal to n plus 1 modulo 5. Okay, and obviously still the domain is this. Okay, and the range is still going to be this. Okay, but effectively, this is a rule that tells us how we computed f of n. Right, so each value of f of n here was obtained by taking my n, adding 1 to it, and then evaluating it mod 5. So what does that mean, mod 5? Well, modulo 5, by the way, is effectively just well, let me write it this way. A number modulo m is just the remainder after dividing that number by m. Is the remainder after division by m. So for example, 11 modulo 5, right, is effectively going to be 1, right? Because you divide it by 5 and the remainder is 1, okay? Because it's 5 times 2 plus 1. So that's really what mods are, right? That's really how they work, is that you just take a number, you divide it by this number here, which we say m, or in this case is 5, and then you evaluate it and it's going to be 1, okay? Now obviously the output of this, right, so anything mod 5, the output's always going to be either 0, in which case it's a multiple of 5, right, there's no remainder, 1, 2, 3, or 4. Okay, so there's only ever 5 options, okay? And that obviously is why, you know, this range set is only ever 5 options. Okay, the input is actually that we can still have the set of integers as our input, right? Because any integer, right, even when you add 1 to it, will still be either 0 mod, either well, and you evaluate it mod 5, will always be either 0, 1, 2, 3, or 4, right? But in this case, we just decided to take this sort of small set, because otherwise we wouldn't be able to write out this table. And I think the point of the example was to show an example of where we could write out just the outputs of a function using a table. Okay, but yeah, in this case, the rule of the function is simply just you take your an input, you add 1 to it, and you evaluate it at mod 5. Okay, so that's really all that's going on there. And whenever we do modular arithmetic, so when we do, this is sort of a side note, modular arithmetic. So modular arithmetic is just basically stuff to do with this with mods here, with remainders. Okay, so whenever we're dealing with remainders, effectively, whenever we do modular arithmetic, we actually define a specific set. So the set that we define is sort of this z with a subscript m, and it's just the set of all integers from 0 all the way up to m minus 1. Okay, and one reason for doing this is so that instead of writing our function in this format here, we can actually say that effectively f is a function from, in this case, z5 to z5, right? Which is just this written in a different way, right? So yeah, right. So it means that this sort of functional form, this sort of way of writing out a function by stating its domain and range, is a lot easier and a lot more compact than this, because here we actually have to state the specific sets. So whenever we're working with mods like this, okay, and our output will be sort of this sort of form, okay, then we always define this specific set, okay, and one reason for that is I mean, I guess because it simplifies the way of writing the function. There's certainly other reasons for it as well, although we don't really necessarily care about those for the sake of the course at this point in time. Just as a side note. Okay, so let me put a box around that. Awesome. So now let's consider a different type of function, which might be a little bit more confusing. Okay, so here's another example, example number 2. Right, consider the function g. Okay, so we'll call it. So we often call our functions saying f or g. Those are typically the labels we give our functions, or sometimes you see h, or you can obviously use anything, but those are the ones we typically use. And in this case, our domain is going to be z4, the Cartesian product of z4 with itself, and our range will be z4. Okay, so this is a bit more of a sort of weird function. Okay, but it's a valid one, right? Because effectively you're just taking an ordered pair and you're just producing an integer from that ordered pair, right? And that's kind of like addition, isn't it? And as we'll see, this is sort of a special type of addition. So consider the function described below, right? And so the way we could describe this function with a table, right, is as follows. So you can do this. So you have your g, and then you put 0, 1, 2, 3. Since that is just z4, z4 is just these elements, right? So our output values will be either 0, 1, 2, or 3, and our input will also be either 0, 1, 2, or 3. Okay, and then we write the table like this. Okay, so this is just what's actually inside the table doesn't necessarily matter, because that's basically, well, it doesn't matter, but it's not really the point of what I'm trying to get at. It's more like what's inside the table is more just what is generated when you do something specific, which I'll explain. So these are just the values. These are like your outputs of the function. So these are here. These are like your outputs. Okay, and so what it's going to look like is 0, 1, 2, 3, 1, 2, 3, 0, 2, 3, 0, 1, and then 3, 0, 1, 2. Okay, so that is effectively sort of a grid of outputs. Okay, and how do we actually obtain these outputs? Okay, so let me just explain that to you. Right, so effectively, well, not necessarily how we obtain them. I will also explain that, but like necessarily, how do we read this table? Like, what is going on here? Okay, because it's not obvious. So the entry in the sort of ith row and jth column, right, is actually just g of ij. So effectively, because remember that we have an ordered pair as our input, right? And so if I look at, for example, let's say the first row, so that's going to be 0, and I look at my first column, so that's I equals 0, and this is my first column. Oh, sorry, I equals 1. Sorry, I mean, and this is my first column, right? Then effectively, or really, I guess I should say 0, because they are starting, I think, with 0 in this case. So this is sort of my 0th row and my 0th column, right? Then effectively, right, this component here, right, so the value that you see at the intersection of those two columns, which will just be 1, one value, in this case is 0. So because of that, we can say that g of 0, 0, so g of that ordered pair is just going to be 0. Okay, and similarly, if I look here, this is going to be my first, my second column, which is effectively, just, we label that with number 1 because we start labeling at 0. So in that case, we have that g of 0, 1 is equal to 1, right? Because the output here, their intersection is 1. So this is that's how we read the table. Okay. So hopefully that makes sense. And actually, there is sort of a neat formula for this. Okay. So effectively, the function can also be written like this. So g of xy, right? Because you have to plug in a sort of ordered pair to it to get an output, is actually going to equal x plus y modulo 4. Okay, so that's actually what this function is. And I mean, the reason for that is because, for example, if I take 1 and 3, so let's say I take 1 and 3, I take their intersection, I get 0. The reason for that is because actually what I'm doing is I'm doing g of 1, 3, which by this formula is just going to be 1 plus 3 modulo 4. And 4 modulo 4 is the remainder when you divide 4 by 4, which is 0. So that makes sense, right? That being a 0 there, that's why it's 0. And that's what you're doing with all of these. So like I said, it's a special type of addition. It's addition modulo 4. Because effectively you're taking an ordered pair, and what you're doing is you're adding the two numbers in the ordered pair to get an integer, to get one number, and you're evaluating that integer modulo 4. So it's like you're doing a little bit of extra work instead of just basically adding them. You're also evaluating them modulo 4. Okay? So that's how that works. Okay. Awesome. So now let's move forward away from the examples of describing functions and more talking about functions. Okay? So when we have a function, so when the function f has a domain which is effectively the Cartesian product of k sets. So it has domain a1 cross a2 cross all the way up to ak. So when my domain looks a little bit like this, okay, so that's just going to be effectively a k tuple, right? If you remember from the last video, it's going to be a k tuple that you're inputting into your function, and you spit out some output, which we don't necessarily know what the range is at the moment. Okay, but whenever the function f has this domain, so it's a k tuple whose first element is from a1, second element is from a2, and so on. Kth element is from ak. So whenever we have this domain, right, for some sets, remember a1 through to ak are all sets, so a1 all the way up to ak, right? The input to f, as I was saying, is a k tuple, and obviously that's going to be of the form a1. So it's like a finite sequence with k things inside it, right? From last time, so that's going to be of this form, right? A1, so two brackets, a1 all the way through to ak, right? And we call a subscript I the arguments to f. Okay, so for example, a1 is an argument to f, ak is an argument to f, a2. So each of the individual a's that I have inside my k tuple, right, is going to be an argument to my function. So this here, this is an argument, and obviously this here is also an argument, right? So every single sort of value inside that k tuple, right, every single element or object is going to be an argument to my function, right, when it has this domain, which is just the Cartesian product of k sets, effectively, not necessarily the same. Right, so then just some more notation here. So a function, so any function, right, with k arguments, right, so for example, the one that we have above, with effectively the domain being the Cartesian product of k sets, because then you get a k tuple, so I have k arguments, right? So any function with k arguments is actually called a k-ary function. It's called a k-ary function. Okay, this is a special name for it. And k is called the arity of the function. Okay, and k is called the arity, so arity, A-R-I-T-Y, of the function. Okay, so that's basically that. So any function that has k arguments is called a k-ary function. So any function with one argument is a one-ary function. Two arguments is two-ary function. Three arguments, three-ary function, and so on and so forth, right? But we actually also have special names for different cases. So for k equals 1, k equals 2, we have special names. So k equals 1, one-ary function is actually the same as what we call a unary function. So one-ary function is equivalent to unary function. So that just means a function with a singular argument, right? And also we have for k equals 2, a two-ary function is actually the same as what we call a binary function. Okay, equivalent to a binary function. Okay, and the last thing to really talk about in terms of functions, I think, or just functions bare bones, is effectively just notation. So we have what we call prefix notation. So prefix notation is effectively what I've been using the entire time today. So that's where effectively you have the function, right? So for example, add brackets, and then effectively the ordered pair that you're inputting to that function, right? Or it could be like abs and then a, for example, these are both prefix notation. But for some special functions, we actually use infix notation. Okay, and actually the books are certain binary functions, because that's typically, that's typically what we use infix notation for. So certain binary functions use this thing called infix notation, and all that really means is that instead of writing add like this, instead of writing the function like this, you have a special symbol that you place in between the two inputs, right? Well, really, both of them are the same input because they come from the same ordered pair, but you see what I mean? From both of the elements in the ordered pair that you're inputting, right? So you put the special sign here, and we just understand this to mean add, right? This basically means the same thing as this. So these two are the same, right? Similarly, for the absolute value, we also have a special symbol, which I'm sure you're aware of, which is effectively just the absolute value of a, right? So that's also infix notation, okay? Because effectively, instead of writing just abs and then a, you have some special notation that you know and understand is representing, meaning the same thing. Okay, so there we go. Actually, I guess maybe they didn't mean that for infix notation, because it said certain binary functions, and obviously the absolute value is not a binary function because it only has one argument, so it's actually a unary function. But I feel like this could be represented in the same way. So yeah, my apologies. Actually, I was slightly incorrect. This is not actually infix notation with sort of the absolute value around the a here. That actually has a different name, so I'm actually incorrect about that. My apologies. But yeah, I mean, hopefully you see the point though. Effectively, infix notation is where you basically just put this symbol in between the two elements of your input. So for a binary function, which is what we're talking about. So for example, multiplication is a binary function, and you use this sort of infix notation here to represent it, right? Similarly with subtraction, division, right? So hopefully you can see where I'm coming from with this infix notation. Effectively, you just put two elements from your input set, right, or from your specific ordered pair that you're inputting, right, side by side, and then you place sort of this operator in between them, which is effectively just representing, the function, right? So in this case, with this symbol here, this operator just represents the add function. Okay, some of the cases would obviously represent the multiply function and things like that. Okay, so it's where you have those two inputs from your ordered pair, and effectively you put this sort of symbol in between those inputs. And that's why obviously this absolute value of a was not prefix notation, because I didn't actually have it in between. First of all, there's not two inputs, and I didn't have it in between them anyway, so it doesn't make any sense. But yeah, I mean, hopefully you get that idea. That we use different notation sometimes. And that prefix notation is like this, where we represent the function formally. So we have this prefix, in this case, and or abs, and then after that we put the thing that we're inputting into our function. We have this infix notation for certain binary functions, where they have two arguments. So this is one argument, this is the other, right? And effectively we just put the symbol that represents the function in between them. Okay. All right. Now let's move forward. So we also have things called predicates or properties. They're the same thing, just different terminology. But a predicate, we say that a predicate or a property, right, is actually just a function, to be honest with you. It is defined as a function, but we have a specific form for its range, right? So whose range is the set, effectively just the set with two elements inside, either true or false, and that's equal to s. Okay, so any predicate is effectively just a function. So what we input into that function is irrelevant in terms of defining it. Okay, but it will always output one of these two things, true or false. Right, so for example, you might have something like has black hair, right? That's like a predicate, for example, right? So then you might input a specific person, and it will say true or false depending on whether the output will be either true or false depending on whether they have black hair, right? Obviously, there's a degree of interpretation. Maybe they have some sort of blackish hair or whatever, but like supposing that we have sort of a well-defined way of saying whether it's true or false, or a way of a way of deciding whether a certain property is a certain thing is true or false, right? Then that's how it works, right? So suppose that we could always say 100% with certainty whether someone has black hair or not. Maybe there'll be like some boundary case where they kind of have black hair and some like mix of different colored hair or whatever. But like supposing that you could obviously 100% always tell whether they have black hair, then effectively has black hair is a predicate, right? Because you just plug in a specific person and it outputs true or false depending on whether they have black hair. Okay. So and another example of this, which is from the book, is effectively this even. Okay, so let even be a property, right? That effectively is going to output true if the input is an even number, right? And false if the input is an odd number. Okay, so every number, right? And obviously, when we talk about number, we're talking about, in this case, let's say integers, right? So every integer is either even or odd. Okay? So, this is always going to work, right? There's never going to be a case where we can input like an integer that just doesn't output true or false, just doesn't know what to put. All right? And so, sort of in action, we can see this, right? So, for example, in action, this would look like even of 4, right? So when I plug in 4 to the even function, right, or in this case the property even, then I'll output true, right? Because 4 is an even number. And obviously 5 is not an even number, so when I plug 5 into the even function of the property even, I'm going to get false as my output, okay? So these predicates, these properties, these predicates or properties are effectively just functions whose range is effectively just true, the set of just two things, true or false, right? So effectively, you put something into it, which doesn't really matter, then the output will always be either true or false, depending on obviously how that predicate works, how that property works. Okay. So looking at this a little bit deeper, we can say that a property whose domain is just effectively a set of k tuples. Say it's just sort of a crossed with a crossed with a k times. Okay, so actually in this case we're talking about what we call a we call it a homogeneous relation, effectively meaning that each of these sets A is just the same. Okay, so in this case we're not dealing with k difference sets, dealing with k sets that are the same, and that's all we'll deal with today. Okay, obviously if these were not the same, we have A1 cross A2 cross all the way up to AK. That we call that a heterogeneous relation, but that doesn't really matter for the sake of this. And there are a few things that don't necessarily work if you have a heterogeneous relation that we actually kind of care about. So we're dealing with homogeneous relations. So we say that a property, right, whose domain is a set of k tuples, right? So a and then just a crosses itself k times, effectively Cartesian product of a k times, which remember we had this notation for a to the power of k, okay, is called a relation. Okay, so it's a special type of property, and it's called a relation. Okay, or we actually call it a k-ary relation, right? So you could either call it a relation, a k-ary relation, right, or a k-ary relation specifically on capital A. Okay, so and the reason we say it's on capital A is because obviously the effectively k tuple that we're going to be producing, each of its elements will be from that set capital A, right? So you sort of increasingly more complicated, but I guess technically increasingly more correct would be you can either call it a relation, a k-ary relation, or a k-ary relation on A. All up to you. It's really up to you what you call it. Okay, but effectively what it's saying is that I have a property, right, which is effectively just something that has a range, that specific range being either true, the second thing in the elements just true and false, the strings true and false effectively. So if I have a predicate, right, which is effectively just like I said, a function whose range is this set, and its domain is a set of k tuples. So effectively, I'm inputting some k tuple, right, and I'm going to always get an output which is true or false. So it takes my k tuple, it looks at it, and it says, okay, does it satisfy the property? If so, then I'm going to output true. If not, then I output false. Okay. So property in that case, whose domain is going to be a set of k tuples, is called a relation. Okay. Great. Now, in practice, right, a case that we see a lot. So in practice, a common case is what is a two-ary relation. Right? And we actually call this a binary relation. Okay. Right. So we typically use infix notation to represent these. So yeah, we just typically use infix notation. And we'll look at an example later. But well, really an example could be something like A is less than B. Okay, this is a relation. Effectively, it's a two-ary relation. It's a binary relation because you input an ordered pair. Say it's going to be AB in this case, right? And then based on how this sort of relation is working, it's going to output either true or false depending on whether A is less than B or whether it isn't less than B. Okay, because one of those two things has to be true. Right? So we typically use infix notation to represent or to really write about binary relations. Okay, or at least typically we do, if I didn't say that. Another example would be equality. So for example, if I give you A is equal to B, that's another relation. Okay, this is actually a special type of relation, which we'll talk about a little bit later, called an equivalence relation. But effectively, it's a binary relation because I'm inputting an ordered pair, AB, into it, right? And then effectively, depending on whether they are actually equal or not, it will output true or false, right? So this is just another example of a relation, or binary relation. Okay? Right. So, now we know what that is, right? Then we can say the following. If capital R is a binary relation, so define capital R to be a binary relation, just some arbitrary binary relation, right? Then, effectively, this sort of notation here, ARB, remember it's a binary relation, so you're only going to have two arguments, right? ARB means, okay, effectively, whenever someone writes ARB, what they really mean is that ARB equals true, okay? So effectively, when I plug A and B into my relation, so effectively just a function, right? And the output of that function is true, right? Because it has to be true or false since it's a relation, right? And the input here is a two tuple, right, or effectively an ordered pair, and so it's a binary relation. Okay. Okay. So this is really just a piece of notation here. A, R, B. So for example, right, obviously the ones that we've seen up there, if I say, for example, 4 is less than 5, what I really mean is that 4 less than 5 is equal to true, because that is true, right? And in that case, obviously, the relation that I'm using is less than, right? That is a relation. But just generally, you could call it R, right? Because we don't necessarily know what it is here. Okay. Cool. And obviously, we can extend this. So if R is a k-array relation, right, then saying something like this, so R, and then sort of placing the k tuple after it, is effectively, this just means that R of A1 all the way up to AK, because remember, R is just a function, right? Only relation is just a function that outputs either true or false, depending on what the inputs are. This has k arguments, so it's a k-array relation. All right, so whenever I write this, or whenever someone writes this, right, what they really mean is that the sort of output of that is equal to true. Okay, so the same thing that we're using up here, but just generalized. Okay. Awesome. Okay, so we can look at an example of how a relation actually works. So let's do that. So here's an example. So in actual fact, we sort of implicitly use relations quite a lot in our lives. Okay, so for example, in rock paper scissors, right? Effectively, two players will just simultaneously select. Well, let me try this down. So in rock paper scissors, two players simultaneously select a member of the set. So there are three options, right, when you're playing rock, paper, scissors. So scissors, rock, and paper. So obviously, the sort of input to that relation is going to have to be one of these, right? It's going to have to be one of these options, right? Because each player can only choose one of scissors, rock, and paper for each move. So at the very start of the game, or at least before you sort of go rock, paper, scissors, shoot, right? You have to decide which of these elements you want to pick. Also, I need to just move this down. Okay, so you have to make that decision. And then based on that decision, what we actually do is we use a relation to determine whether, who's won, basically, right? Because you need to have a way of deciding who won the game. And actually, you can use a relation to do that. Okay, but let me just finish writing that. Okay, and obviously, once you've picked one of those options, obviously you indicate which one you've picked by using the hand symbol. So rock, paper, scissors, stuff like that. And you indicate their selections with hand signals. Okay, so if there are two selections, so effectively, if both players select the same option, so if both players select scissors, then the game starts over. Two selections being the same means that the game starts over. So you just redo it, basically, if both of your options are the same, right? Two different selections, though. Two different selections. So if someone chooses, if one player chooses scissors and the other player chooses rock, for example, then that means that one player will win. Okay, so definitely one player will win. Okay, and actually, how do we know which player wins? Well, actually, they win according to the relation. According to the relation beats. So actually, it's a binary relation because it has to take both player one's input and player two's input. So it has to take whether player one inputted scissors, rock, or paper, and whether player two inputted scissors, rock, or paper. Okay, so we call this relation beats, just a function taking the two players' inputs and then outputting true or false depending on effectively which player wins, right? I mean, well, if that doesn't make sense, I know that's a little bit vague, but let's just go through sort of how this relation would be defined. So let's look at it here. So we can use a table to define this relation in the same way, because relations are functions, so you can use a table to define it. And effectively, in this case, we have three options, so three inputs. This is like player one. So this is like player one. This here is player two. So you're going to have scissors as well, rock, paper. You're going to have rock, paper. And then obviously, so you input into B. So it's a binary relation. So you input an ordered pair. So for example, you'd always input player one option followed by player two's option like this, right? So this is just an ordered pair, right? So if player one goes for scissors and player two goes for scissors, then false is the output. In other words, effectively, neither player wins in both cases, right? Because so if player one goes scissors, player two goes scissors, then player one loses, right? And if player 2 goes scissors and player 1 goes scissors, then player 2 also loses. Okay. Okay. And if player 1 goes scissors and player 2 goes rock, okay, then player 1 will lose, okay, because rock will beat scissors, so then that's going to be a false, right? And if player 1 goes scissors and player 2 goes paper, right, then player 1 does win, so that's a true, okay? If player 1 goes rock, player 2 goes scissors, then player 1 does win. Player 1 goes rock, player 2 goes paper, paper beats rock, so that's false. And obviously, rock and rock, that's the same, so both ways that's a false. And then rock, paper, that's also going to be false, because paper beats rock. Okay, and filling out the last part of the grid, so false, true, and effectively false. Okay, so effectively, well, when I say player 1, what I really mean is just like one player's option. So like the player that your option basically. So for example, if your option was scissors and your opponent's option was rock, then you would look at effectively beats, so that's the relation, and then you would look at the ordered pair scissors, rock, and you would see whether or not it's true or false. In this case, it's false. So if you played scissors and your opponent plays rock, then that's false. So this is how effectively this relation is working. It's telling you, so if it outputs true, then that means that if you were to play scissors, for example, and your opponent played paper, you would win. So true effectively indicates winning, and false effectively indicates losing. Okay? But you could also read it as player 1 and player 2. That might also be confusing, because then you might be like, oh, if I was player 2 and I play rock and player 1 plays scissors, then does that mean that I lose because it's a false here? No, obviously you win that, but like we're talking about in player 1's perspective. So just to make that very clear. Okay, so effectively, what we can see, so beats, so this relation evaluated on the ordered pair rock scissors, right, is obviously going to be equal to true, and we determine that rock beats scissors. Right, and obviously similarly, what you can see is that paper beats rock and scissors beats paper. Okay, so those are two things that can be seen, because if you were to look at beats and then the ordered pair paper rock, right, you would see true. So paper beats rock, and same with beats scissors paper, right, you would see true. Okay, right. So last sort of bit to talk about, well, almost last bit to talk about. If I have a predicate, so the predicate P, which is obviously just a function whose domain is D and whose range is going to be always the set containing the elements true and false, right? So this is a predicate. So the predicate P from D to the set true false may be written. So another way that you can write this is effectively as an ordered pair itself. So DS like that, okay, where S is equal to the set of all effectively input values, such that effectively when you plug them into your predicate, you get true as an output. Okay, so this is just another way of doing it, right? So for example, if for the above game, so for the rock paper scissors game, right, you might be able to just write your effective. You could write effectively write the predicate instead of actually stating the predicate like this and then explaining sort of how it works via a table. You might, you can. It's also okay. In other words, it's fine to write the predicate in this form here, where effectively you put the domain as the first element of this ordered pair. So effectively, obviously, your domain is going to be the set. It's going to be a set of ordered pairs. So in that case, it's going to be scissors, paper, right? Scissors, rock, scissors, scissors, and then like it's just a Cartesian product effectively of, well, in this case, actually, let me just write it like that. Actually, so it's going to be scissors, paper, rock, and the Cartesian product of that with itself, right? To get all possible like combinations of moves effectively in the game. Right, so that's your domain. So that would be your D. And the second element of your ordered pair would be all the things that evaluate to true, all the possibilities that evaluate to true when plugged into your property. So in our case, what would that have been? That would have been so scissors beats paper, paper beats rock. Sorry, what am I doing here? That's supposed to be an ordered pair. Paper, rock, and then rock, scissors. Okay, so this is just another way of effectively displaying, should need to put another bracket there, of effectively displaying the predicate, right? So if you wanted to, instead of like formally giving the rules for the predicate, right, you could basically just give the domain of it, right, and then just give all the sort of elements of your domain that are going to basically give an output of true when plugged into the predicate, right, and you can have that as an ordered pair, right. So in this case, our domain is the cross product of the set scissors, paper, rock with itself to get all possible combinations of like input moves from players, and the sort of output from that is effectively just all the winning combinations. So scissors beats paper, paper beats rock, and rock beats scissors, right? Okay. So last thing, this is actually the last thing, is equivalence relations. So a binary relation, okay, and for now we'll just think about this with binary relations. So binary relation R is said to be, so is called an equivalence relation. An equivalence relation if, right? So first of all, R is reflexive. Okay, so you might wonder, what does that actually mean? What's going on there? Okay, what that means, so this means, what that means is effectively that every X, right, in your set A, because obviously your relation is effectively like, a binary relation is going to be effectively a function from effectively A cross A, or remember we're talking also about homogeneous relations, so these two sets have to be the same, effectively from A cross A to the set true, false, right? So obviously the relation, the binary relation is going to be of that form. And so all we're saying is that for every X in capital A, okay, X is sort of related to itself. So X R X. And that effectively just means X R X equals true, right? So for example, if my relation was effectively the equals, so effectively with the equals relation, okay, so equals relation, we obviously have that if, let's say A is equal to the integers, right? And obviously, for example, so every single integer is equal to itself, right? So for example, 4 is equal to 4. Right? And to be fair, you would hope that something, the equal symbol is an equivalence relation, right? When you just, without even really knowing what it is. And so yeah, equals is an equivalence relation. And this is one of the reasons why it is because it's what we call reflexive. Because if my set A was an integer, the set of integers, right? So wherever it's defined, so on any set of which the effectively equals relation is defined, any set capital A where the equals relation is defined, and it's a homogeneous relation because we have the same A, so A cross A is the same set. On any set where it's defined, every single element of that set is related to itself, okay? Because 4 is equal to 4, 5 is equal to 5, so on and so forth. Okay, so that's what it means to be reflexive. And then we also have two other notions. So the second notion is that it's symmetric. So R is symmetric. So what does that mean? So this means that for every X and Y, because we need two different variables here, for every X and Y in the set capital A, okay, X R Y implies Y R X is true. Okay, so effectively, if X is related to Y, then Y is related to X. Okay, so again, this is true for the equals relation, right? So for the equals relation, X equals Y, right, implies Y equals X. Implies Y equals X, right? Right, because if X equals Y, then certainly Y equals X, right? So so that's just symmetric. That's what it means for a relation, a binary relation, to be symmetric, right? And thirdly, we require this thing called transitivity. So R is transitive. So what does that mean? So this means that for every X, Y, and Z in capital A, right? If X is related to Y, and Y is related to Z, then X is related to Z. Then X is related to Z. Okay? Effectively, another way of saying that is that if X is related to Y and Y is related to Z, that implies, so X related to Y, Y related to Z implies X is related to Z, right? So what I should really say here is that if X is related to Y and Y is related to Z, then X is related to Z. Okay? So again, another example here is the equals relation, right? So if X equals Y and Y equals Z, then certainly X equals Z, right? Yeah. It might seem quite simple, right? Obviously, if 4 equals 4 and 4 equals 4, then 4 equals 4, right? Like if you say it like that, then it's sort of stupid. But in math, we don't necessarily always have, like you could have two expressions that are the same thing, right? Or we say that those two expressions are the same. So for example, you might have something like x squared plus 4x plus 2 is equal to 5, right? So in that sense, you have a sense of equality, but it's not just 5 equals 5, it's something else equals 5, okay? And maybe you have three expressions that are equal to the same thing, and so you can use transitivity to effectively say those two are equal and those two are equal, then that must be equal to that, and you can like have a look at another way of them being equal. I can't really think of a good example off the top of my head, but you do use this quite a lot, right? Hopefully you understand what it means to be transitive. It's just that if x is related to y and y is related to z, then x is related to z, right? So for example, if x is equal to y and y is equal to z, then x equals z. But yeah, I mean, we do use this actually quite a bit implicitly, but it's fairly straightforward to understand, right? But these properties are really what defines equivalence relations, okay? Of which obviously equals is an equivalence relation because it has all these properties. The equivalence is a binary relation, right? You have to sort of input an ordered pair, right? And obviously the output will be true or false. True if they're equal, false if they're not. And obviously it satisfies all of these properties. So it's reflexive, symmetric, and it's transitive. Okay. Okay. So now let's go through one last example before finishing, which is effectively just a question. So question. Okay. So define a binary relation, right, on the natural numbers. Okay. And we're going to denote it with this sort of three sort of parallel lines here, and then a subscript 7. Okay. So for any two natural numbers I give you, so for I and j in the naturals, right, we say that effectively I, these three sort of parallel lines, subscript 7, j, so I is related to j via this relation, right, if I minus j is a multiple of 7. So that's how this relation works. Okay, so it's just a special relation that you've defined. Okay, and the question here is we need to show that this is that effectively 3 parallel lines subscript 7 is an equivalence relation. Okay, specifically. So how are we going to do that? Well, in order to do that, right, and just going through an example while we do it, you need to prove those 3 properties, that the relation satisfies 3 properties. One, that it's reflexive. Well, first of all, it needs to be binary, which it is already, right? It's a binary relation because you have two, you input an ordered pair, okay, and then you can look at that ordered pair, do one of the elements minus the other, and see if it's a multiple of 7. If so, then true is outputted. If not, then false is outputted. So it is a binary relation, that's fine. But we need to show it satisfies these properties, okay? These 3 properties. So first of all, is it reflexive? Okay. So is it true that, for all natural numbers I, is I sort of 3 parallel lines 7 to itself? Right? So is it related to itself via this rule? Well, yes, right? This is true, since obviously I minus I is equal to 0, which is a multiple of 7. Okay, so the relation is reflexive, right? And this obviously holds for all natural numbers, because any natural number minus itself is 0. Okay, and next we need to show it's symmetric. Okay, so that was fairly straightforward. Symmetric is a little bit more tricky, but the same kind of idea. Okay, so suppose, for this one you have to say suppose that I is related to j by this relation, right? Right, and if that's true, then we know that I minus j is equal to 7k, or in other words, a multiple of 7 for some k, say in the in the natural numbers and the integers. Actually, it doesn't necessarily have to be the natural numbers, because we could have 4 minus 10, for example, right? So then for some k in the integers, right? Okay, and so that's definitely true if they're related by this rule. Okay, so what we can say is that j minus I is equal to effectively minus 7k, because you basically just took out a minus sign, right? I minus j times minus 1 is j minus I, so you can multiply the right hand side by j minus 1 as well, right? Which we can say is equal to 7p, for p is equal to minus k, which is obviously in the integers, right? And so this is just effectively the same rule, right? So j minus I is also a multiple of 7, right? So effectively j is also related to I by the same relation, okay, as required, okay? Because all we need to do to prove that the relation is symmetric is suppose that I is related to j, and then show that implies that j is related to I, which we've done, okay? And then lastly, we need to do transitive, okay? So suppose that I is related to j by this rule, and that j is related to k by this rule, okay? So I minus j is equal to 7k for k in the integers, right? And j minus k is equal to 7q, right? Because j and k are related via this rule for q in the integers, right? So this is just given to us because of the fact that we are supposing that I is related to j and j is related to k. So notice that I minus j, right, plus j minus k, right, is equal to I minus k, right, and it's also equal to I minus j is also equal to 7k, so 7k, and j minus k is 7q, so 7k plus 7q, which is 7 multiplied by k plus q, which is effectively the same thing as 7p, for p equals k plus q, which is in the integers, right? So I is also related to k by this rule, showing that the relation is transitive. Okay, and then we're basically done, right? Because effectively binary relation, so 3 parallel lines subscript 7 is reflexive, symmetric, and it's transitive. Okay, so it's an equivalence relation. As required. Okay, and that's that, and that's actually the end of the video. Okay, so thank you guys very much. This is probably going to be quite long when it comes out because there's quite a lot that we covered here, in terms of functions and relations. But it's all very critical stuff. It's all a prerequisite to the theory of computation. So please do make sure you're happy with everything that's been in the video. A bit more dense in theory than the previous videos, previous prerequisite videos, but certainly important. Well, yeah, and so yeah, it is more important, right? More dense in theory, and the theory is a little bit more complicated. So yeah, I would say this is probably the most important stuff we looked at so far. Okay, next video will be on graph theory. Okay, still prerequisites, but next video will be on graph theory. Thank you guys very much for watching, and I'll see you guys in the next one. Goodbye.